So today's lab is all about glassware. In class we learned about the different types of glass and the different types of glass equipment that we can use in the lab for measuring. And the large majority of the measurements that we will make will be volumes of liquid. And so the lab today is going to involve identifying types of glassware. As you look at your lab handout, there are 9 setups or stations that you will need to perform some type of task having to do with glassware, and station 1 through 5 have to do with identifying these types of glassware. So the first station has this piece of glassware here, and this is our volumetric flask. And the volumetric flask is going to be used for making solutions, and it is very precise. And we talked in class about how it's very precise because it has only one marking on it, or one measurement. This one is specifically going to measure 250 mLs. So when you fill out your lab sheet, you're going to put the type of glassware, its use, and whether it is volumetric or non-volumetric, and whether it's precise or non-precise. The second piece of equipment, or station 2, is our graduated cylinder. This is used for measuring liquids. It is volumetric and it is precise, but it's not as precise as the volumetric flask. The reason it's not as precise is because it has more markings or more measurements along the side. Every time you add an additional marking or measurement during calibration, you are introducing potential error in your measurement. Station 3 has a Griffin beaker, or a low Griffin beaker, and this is used simply for holding liquids. It is not precise, and it is not considered a volumetric piece of equipment. While it does have markings on the side, and it does have a milliliter volume that can be measured in it, this measurement is not going to be accurate enough to be used in making solutions in the lab. It is simply a holding container, and we can estimate the volume that is inside of that container. Station 4 is our Erlenmeyer flask. Again, the Erlenmeyer flask is non-volumetric and it's not precise. It is simply used for holding liquids, and you can estimate the volume of liquid that you have in that container. Station 5 shows us several variations of a test tube. Test tubes are usually made of glass and they are disposable. There are smaller test tubes that are used for some types of testing in the lab, and larger test tubes that are used for other types of testing in the lab. They are also used for holding liquids. You can tell that there are no markings along the side of them, so they are non-volumetric and they are not precise. They are simply going to be used to hold or move smaller volumes of liquid from place to place in the lab. Station 6. Station 6 actually has 2 volumetric flasks, and it is asking us to determine in container A or in container B whether or not we have an accurate, specific volume of liquid inside of the flask. These flasks are both marked to hold 250 mLs, and they have simply the single marking along the narrow neck for that simple volume. Remember, as we talked about in class, whenever you are going to be reading the volume, you are going to be reading the volume of liquid at the bottom of the curved surface of the liquid called the meniscus. And you do need to get at eye level to do this. So if you look at the first volumetric flask, we do have a meniscus that is sitting directly on the 250 ml mark, so it does contain exactly 250 mLs. The second container, however, and I'll point to the line, actually contains an amount of liquid that falls above the 250 ml mark, and we have no idea how much liquid is actually being held above that mark, so it does not contain a specific volume of solution. Station 7 has several graduated cylinders. And these are often used in the lab to measure volumes of liquid, as we mentioned before. In each of the graduated cylinders, we need to determine the smallest value or subdivision of the milliliter that we can actually read using that graduated cylinder specifically. So A has a 10 milliliter graduated cylinder. And if you look very closely at the markings on this graduated cylinder, you can see that the 10 milliliters, which is listed at the top, is then subdivided into 1 milliliter increments. So we have 9, 8, 7, 6, all the way down to 1. In between the number markings, there are some additional markings. And I can count that there are 1, 2, 3, 4, 5 markings in between each of the numbers. That would mean that if we had 1 milliliter divided into 5 subdivisions, or 1 divided by 5, each line in those subdivisions represents 0.2 milliliters of volume. Graduated cylinder B is a 25 milliliter graduated cylinder. So you can see 25 at the top. But unlike the first graduated cylinder we looked at, this one is divided 25, 20, 15, 10, and 5. So it's divided by 5 milliliter increments. In between those increments, there are some longer and shorter subdivisions as well. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 actual divisions in between those numbers that are 5 milliliters in difference. So if you take 20 milliliters to 25 milliliters, or a 5 milliliter increment, and divide it by 10 markings, you would get 0.5 milliliter increments in between each one. C is a 50 milliliter graduated cylinder. This one, again, is divided by 5 milliliter increments, but in between these, there are only 5 markings between 45 and 50, or between 30 and 35, for example. So if you take 5 divided by 5, that would be 1 milliliter increments. Graduated cylinder D is a 100 milliliter graduated cylinder. This one has divisions of 10. So you see 50 to 60, 60 to 70, 70 to 80, and so on and so forth. And in between, those are again divided into 10 markings, or 10 divisions in between. And 10 milliliters divided by 10 markings would represent 1 milliliter increments. Graduated cylinder E is even larger. It is a 250 milliliter graduated cylinder. This one is divided up into 20 milliliter increments. And in between each of those, there is a division directly in the middle. So you can see directly at 10 milliliters in between each division. And then in between those, again, there are 5 additional markings. So if we take 20 divided by 10, we would get 2 for our answer. That means each mark is a 2 milliliter increment. Our last graduated cylinder, F, is a 500 milliliter graduated cylinder. It is divided up by 50 milliliters. And in between each of the 50 milliliters, there are 10 additional markings. So 50 divided by 10 is 5, indicating that each marking is showing us a 5 milliliter increment. Remember that when you're measuring liquids with a graduated cylinder, you're going to want to choose a total volume or a size of a graduated cylinder that is closest to the volume you're trying to measure. So if I'm trying to measure a 10 milliliter volume, I'm going to want to choose the 10 milliliter graduated cylinder, or something as close to that as possible. I do not want to choose an extremely large graduated cylinder like the 200 or the 250 if I'm measuring just a small volume. The closer the overall size of your cylinder is to the volume you're trying to measure, the more accurate your measurement is going to be. Station 8. We see again a series of graduated cylinders, but in this case they actually contain a volume of liquid. Remember that when you're looking at the volume of liquid in a container, you have to get down at eye level and look directly at the bottom of the curved meniscus at the surface of that liquid. Then you will be able to tell exactly what volume is inside of that container. So for A, we have a 10 milliliter graduated cylinder, and if we get right at eye level and look at the bottom of the meniscus, it is actually sitting on the 8 milliliter line. For B, we have a 25 milliliter graduated cylinder, and the bottom of the meniscus is sitting directly on 19 milliliters. The next one, C, is a 50 milliliter, and the bottom of the meniscus, that curved line at eye level, is sitting on 39 milliliters. D is a 100 milliliter graduated cylinder that contains exactly 75 milliliters. E is a 250 milliliter graduated cylinder, and it contains exactly 200 milliliters of liquid. And I want to point out at this point, this is a plastic graduated cylinder. Whenever we have plastic graduated cylinders, you can tell that the curved line at the surface of the liquid is not quite as curved as when we have a glass container. It's also not as curved as the width of that device gets wider. Our last graduated cylinder is 500 milliliters, and it contains exactly 400 milliliters of liquid. The last station that we have for lab today is showing us some serological pipettes. And we talked in class about how serological pipettes are accurate and they are volumetric, and they're used to measure smaller volumes of liquids when we're trying to move that liquid from one container to another. It's also important to be able to tell what each marking on the side of the pipette is indicating when it comes to the volume in milliliters. So for serologic pipette A, we have a 1 milliliter pipette, and it tells us here that it's divided up into tenths. So we have 0.1, 0.2, 0.3, 0.4, 0.5, all the way down to 1.0. In between each of these numbers, there are 10 additional divisions. So if we take 1/10 of a milliliter and divide that by 10, we would get 1/100th of a milliliter. So each marking indicates 0.01 or 1/100th of a milliliter. And it also is indicated at the top, 1 per 100 of this 1 milliliter pipette for each marking. The reason that 0 is on the top of our pipettes is because when we fill a pipette to move a liquid, we are always going to fill the entire pipette all the way to the top marking, and then we can measure out the specific volume that we need, and we would be counting from top to bottom as we empty the pipette into our new container. Serologic pipette B is a 2 milliliter pipette. It is divided up into 0.2 increments, and in between each of those increments is one additional marking right in the center. That means that each marking on this pipette indicates 0.1 milliliters. Serologic pipette C is a 5 milliliter pipette, and it is divided into 1 milliliter increments. Those are further divided right in the center, and then further divided into 5 increments. So between the 2 and the 1, for example, there are 10 markings, which indicates 0.1 milliliters for each mark. The next serologic pipette D is a 10 milliliter serologic pipette. It again is divided by 1 milliliter, And again, right in the center with a larger line. And then with smaller lines, it's divided into 5 additional sections. So between the 4 and the 3, or between the 3 and the 2, there are 10 markings dividing up that 1 milliliter. This one again indicates 0.1 milliliters for each marking. Our last serologic pipette is a 25 milliliter pipette. It is again divided into 1 milliliter increments that are further divided into 10 increments. And so again, this pipette has 0.1 milliliter divisions or markings.